Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Okay, let us continue our discussion on dislocations. In the last class, we looked at again different kinds of interactions between the dislocations, and also kind of mechanics of dislocations, I would say, in terms of dislocation generation and its interaction with obstacles and so on. Right? In that connection, we are going to continue our discussion on the dislocation intersections. We looked at interactions, and now this is intersections between two line dislocations, right? So the number of dislocations increases as the deformation proceeds, and the increased number makes their movement become more difficult. Okay. As I mentioned in the previous class, we are now getting into details of deformation. So, though we are yet to address that, but in the context of dislocation and its multiplication, we are indirectly discussing the plastic deformations. So the number of dislocation increases as the deformation proceeds. That means as you continue to deform the material in below recrystallization or the cold deformation, the increased number makes each dislocation to move further. Okay, so it becomes difficult because of the interaction between other or neighboring dislocations. This increased difficulty of movement is caused by the intersection of dislocations moving on different planes. So we were talking about dislocation, cross-lip, dislocation, claim, interaction with one dislocation with the other. Okay, so all these things will have some impact on the dislocation density. For example, I also mentioned about the wavy slip and planar slip and so on, where when we talk about a wavy slip material, we are connecting the mobility of dislocation in 3 dimensions. That means the dislocation motion is not restricted or confined to a given plane. For example, that is what happens in the planar material, planar slip material. But in a wavy slip material, the dislocation moves freely all over the place. But 3-dimensional motion is not restricted. So in such cases, when the density of the dislocation increases, obviously they will encounter the other dislocations. And the number of dislocation lines per unit area increases, then the difficulty arises in terms of motion. So during easy glide, the rate of work hardening is low because slip occurs on a parallel planes and there are few intersections. Okay, we are now bringing another term, work hardening. We will, in fact, we are going to address this terminology. This term will surface when we discuss the cold work of material and one of the strengthening mechanisms. This will come as a part of the content, but here it is closely related to the room temperature deformation or cold deformation. So here the rate of work hardening, so that means it is also related to the dislocation density and its interaction. So that's why it is here. So during easy glide, the rate of work hardening is low. That means when there is no high density of dislocation, the glide is enabled without any problem in a glide plane. Then the work hardening rate will be low, sorry, not slow, low. Because the slip occurs in a parallel planes. The slip, we have all the possible planes which are favorably oriented. Here in this case, all the parallel planes, we are assuming that they are all favorably oriented. So the dislocations will try to move in those parallel planes. And then the intersection will be minimal. That is what it is. As soon as a slip occurs on more than one set of slip planes, dislocations on different planes will intersect, and these intersections impede further motion, causing rapid work hardening. Okay. So a slip occurring at few slip planes, possibly a parallel slip planes, then the glide is easy, not impeded by any other dislocation. But when we are talking about multiple slip, that means several slip planes are activated, where all the slip planes will move in different directions depending upon the easy glide orientation and so on. We will see which orientation will enable easy glide of dislocation and so on. So once those additional slip planes are activated, the dislocation motion takes place in all the randomly oriented planes. Then obviously one would expect that these dislocations will try to interact with each other, and then it will impede the motion of the other. So that is where the restriction comes into play, and that is an indication of work hardening. So which is here we are talking about rapid work hardening. That means, as I said, that the dislocation moves with a velocity, very high velocity. Right? That's what we discussed in the previous. The velocity is very high. So that's why the interaction also will be very rapid and results in rapid work hardening. The nature of dislocation intersections can be understood by considering several types of intersection in a simple cubic crystals as illustrated in figure. So this is one set of schematic. We are going to look at it. Very simple case we are going to assume, and then try to understand what kind of impact it will create. Right? When two dislocations intersect, a jog is created in each dislocation. So we are now getting into a new term, jog, in a dislocation. Two dislocations intersect, a jog is created. Okay, so jog is a typical name given when the jog results only by the as the consequence of intersection of two dislocation lines. So that way we can remember this. So the direction of the jog is parallel to Burger's vector of the intersecting dislocation, and the length of the jog equals to the magnitude of the Burger's vector of the intersecting dislocation. So this is some characteristic of a jog. Okay, so this is the figure we were referring in the previous slide. So we will concentrate one by one. There are too many figures at one time, so it is it's better to spend some time to understand the figure first, and then we'll get into the concept. The unit cell which is drawn here, this is before intersection. There are two dislocation lines are drawn, A and B. If you look at the A, the edge, you can clearly see that edge dislocation sign, right? This is edge dislocation, and side the B also you can see that the edge dislocation is there in the positive edge dislocation. Okay, and A, top as well as bottom, it is positive edge dislocations. Now these two arrow indicates the direction of the motion. Okay, that is trying to respond to the stress, external stress or whatever it is. It is a direction of this two dislocation line. They move in these directions. B is moving, coming out of this unit cell, and it is going inside the unit cell. So this is before intersection, and this is after the intersection. What you are seeing here is the dislocation has surpassed. That means the interaction intersection takes place, and then it produces a jog here, the B dislocation here and A dislocation here, and then they just surpass each other and then create a jog, and then it starts moving further. But if you look at the next figure here, let me check something is happening to the recording. Oh. Yeah. So if you look at this, the second figure, where already a screw dislocation is generated, and then you see the dislocation line C and D, and then look at their direction, and if these two dislocations are trying to move in the presence of a screw dislocation like this, then after they intersect, what happens? You see that it produces a jog here, and there again there is no problem. The jog will move in this direction, or this jog will move in this direction depending upon the force. But what resulted of the intersection is shown here. So still that line is moving in that direction, this line is moving in this direction. But third case is quite different. You see that the screw dislocation is created here, and there is another screw dislocation perpendicular to this unit side. Now the dislocation line E and F are in a very different situation as compared to A, B, C, D, these two cases. So this is a before intersection, after intersection. So you see that as the intersection proceeds, then you see that the jog which is created here on E and F are shown here. They are not similar jogs, or their motion is not similar to the previous jog motion, because we will see why. So for dislocation A and B in figure, the jogs create no problem. If the upper part of the dislocation A and the right side of the dislocation B move slightly faster, the jogs will disappear. Okay. The same is true for dislocation C. If its left side moves faster, it will disappear. Okay. The jog in dislocation D simply represents a ledge in the extra half plane, and it can move with the rest of the dislocation. Okay. Here we are talking about the D. Okay. However, the jogs in dislocations E and F cannot move conservatively. We are talking about E and F. These two jogs will not move conservatively, because you see that enlarged view of this E and F is given. There the shear stress which is acting on these two lines are also shown here, and the enlarged view of this ledge is shown here. So this is going to move this direction and this direction, and this ledge is going to move this direction and this direction depending upon the direction of force. Okay. These jogs have an edge character, and the direction of the motion is not in their slip plane. This is the problem. Okay. If the direction of the motion is not in their slip plane, and they are going to encounter each other, because you see that this plane, that shear, screw dislocation on this direction is going to come this direction, move in this upward and this direction. That means two screw dislocations move in a perpendicular direction, then this jog will get, we'll get into a very special situation. Okay, what is that situation? So this is the continuation of those jogs. So this is a jog. This figure shows that a continued motion of this jog dislocation would force atom into the interstitial positions. Suppose if the jog goes like this and then another jog comes in the opposite direction, they will force interstitial atoms to get into this void. Okay, and there is another possibility. It can also produce something different, like what is shown in figure B, that jogs of opposite sign, they produce vacancies. Okay, so here it is shown a vacancy here. So here it is an interstitial and here it is a vacancy. So there are two possibilities. Okay, either they can get locked on in interstitial solute atoms or they just can create a vacancy. So this is what's shown in both E-type jogs and an F-type jog, which is shown in the previous slide. So this is again an interstitial and this is a vacancy. Just to continue that, if the intersection had been in the opposite direction, movement of jogs would have create a row of vacancies. Suppose in the line of dislocation, we said that the opposite jogs will create vacancies. All of them would result in a line of vacancies if this kind of ledge formation continue to move in the opposite direction. Okay. So to give a idea of what happens in a boundary like this, and this is a ledge, a dislocation boundary, it forms a ledge which is similar to what is produced here, jog, and these positions will get either, as I said, either it get locked by interstitial or it will create a vacancy. So that means it will get pinned down by these points, all these points, right? So there will be a drag, and then we know the line tension, all this, this is how the dislocation moves and so on. And then finally, it will produce a vacancies like this, and then as it moves. Okay, so that's what is written here. If the intersection had been in opposite direction, movement of jogs would create a row of vacancies. This is a row of vacancies. But it is not going to happen so easily because energy consideration. If you discuss that, high energy is required to produce a row of interstitials. Therefore, an interstitial producing jog will likely to be pinned rather than produce a row of interstitials. Okay. So this causes a drag on any motion of the dislocation, like what we have seen in this previous image. So we are now talking about two types of jog: interstitial producing jog or vacancy producing jog. Intersections causing interstitial producing jogs are geometrically much more likely than the intersection causing vacancy producing jogs. The reason for this could be understood in terms of the slip systems likely to be simultaneously activated. Okay, so to explain this, whether the interstitial producing jog will get produced or the vacancy producing jogs will get produced, we have one schematic here. What is the schematic shows? The schematic showing why interstitial producing jogs are more likely than the vacancy producing jogs. We will see. Figure below illustrates this. for a crystal with two slip systems oriented at 45 degrees. So this is one slip system, this is another slip system, to the axis of tension, or it could be compression. In this case, it is tension. The intersection of these slip systems will create only interstitial producing jogs. In real crystals, it is possible to find the stress states that can activate slip system that will create vacancy producing jogs, but they were fewer than those that create interstitials. So what it means is when you have the real systems, the interstitial producing jogs will be the most prominent case as compared to the vacancy producing jogs because of the, again, an energy consideration. And what practically will happen is, because most of the real systems will have some or the other impurities, interstitial atoms, and so on. So that is another reason why it is preferring to produce this. With the multiple intersections, the number of pinning points increases and the stress to continue moving the dislocation increases. So the intersection we talk about as the dislocation density is increasing, and then when you have the intersection causing pinning this second phase particle or a solute atoms or interstitials here we are talking about, that increases. They are all anchoring points. That means whatever the jogs produce, they are already locked up. So that means it will act as an obstacle for the other neighboring jogs or any other dislocation to move around. Okay. These intersections act as anchors, greatly decreasing the mobility of the dislocation. As the number of dislocation increases, the frequency of intersections also increases, making further slip more difficult. So this kind of mechanisms give you a perspective of why the dislocation density is directly promoting work hardening. So whatever the mechanics we are just discussing, it is completely related to the work hardening nature of any given material. Okay. So finally, we talk about Klein. We have already discussed this in terms of dislocation motion, and here the schematic shows the extra half plane. In one case, it is extending downward. The other case, it is moving upward. So there are two possibilities: either it can come down or it can go up. And we have seen that the movement of an edge dislocation out of its glide plane can occur only if there is a net diffusional flux of atoms away from or to the dislocation. Such motion is called climb. If you recall the previous climb slides, we have shown some vacancies which is trying to get attracted towards this dislocation core, and in that case the atom will go and occupy that vacancy. That means the extra off plane is going up. That is climb. That's a positive climb. Or the vacancy is started moving away from this core and the atoms are coming here. That means the dislocation climb is downward. Okay. So the removal of atoms from the dislocation causes upward climb, and the addition of atoms to the dislocation causes a downward climb. Both are equally possible depending upon the characteristic of a material. Very important point is, because climb requires diffusion, it is important only at elevated temperature during creep. Okay, so this particular mechanism of dislocation climb is quite relevant to the creep. When we discuss the creep mechanisms, we will use this terminology of or the aspect of dislocation. Diffusion controlled climb allows dislocation to avoid obstacles that impede their glide and may become a controlling mechanism during creep. So this is again a very important point. Diffusion controlled climb is also a mechanism of a creep, at high temperature deformation. We will use this or we'll bring all these aspects when we discuss it. So this is kind of a mechanics aspect of dislocation. That's why I brought it now itself, though it involves a lot of plastic deformation. Those things we can connect it later. But if you look at purely the mechanics part, it in all these activities, whatever we have of dislocation we have seen, it very suitably, suitably illustrated the dislocation nature.